Hello, this is 1.19 Evidence, Angles, and Proof. Today, we're going to be able to label and make conjectures from diagrams, and also prove vertical angles are congruent. Go ahead and pause the video and do this warm-up. It's asking you to measure all the missing angles in each figure with a protractor. So I can see that this angle right here is 50. If we lay our protractor on top of that, I can see that it lines up with 130, so this angle is 130 degrees. This angle is 30 degrees. I can line up my protractor and get the one directly next to it. I can see that that lines up with 150. There's also a little angle here. Can line up our protractor and see that that lines up with 30 degrees. So this one's also 30 degrees. And then if I spin my protractor around, I can see that that angle on the bottom is also open to 150. Next, this one, if we line it up, if I extend this line, I can see that it's passing right between 110 and 120. If you extend the line, you can prove it that it does in fact go through 115 and 120, or 110 and 120 right there at 115. And then on this one, this angle that's open wide here, it looks like it's passing a halfway between 140 and 130, but we can extend the line and prove it. Yep, it's going right there, right in between at 135. Then we can measure the small angle next to it. It's also passing right between 50 and 40, so it's at 45. And then this last little one, it's passing right between 40 and 50, so 45. Now, before we continue on today, take a look at these angles and see if you notice some patterns. We've got a 130 and a 150, 30, 30, 150 and 150, 115 and 65, 135, 45, 135, 45. So as you can see, these two pictures are intersecting lines, and these two pictures are just straight lines split into two angles. So thinking about how you could calculate these without using a protractor, we can already start noticing that when they're on a straight line, look at what they add to. 130 plus 50 is 180. 115 plus 65 is 180. So on this diagram, if I had wanted to calculate 130 without a protractor, we could have calculated 180 minus 50, which is 130. We would not have needed our protractor, but we did prove it using our protractor. Same thing here, 150 and 30, so 180 minus 30 degrees is 150, so I can calculate that angle there. Same process with these two. 180 minus 65 is 115. And same thing here, 180 minus 135 is 45. So you can use your knowledge of what's called straight lines or straight angles in order to calculate missing angles in diagrams. Let's give some vocabulary to each of the things we just talked about. The first thing that's true, or first vocabulary word we want to define, is a straight angle. Well, a straight angle is a straight line, and it measures, a straight line measures 180 degrees. Every straight line, so if we draw a straight line, I put some point here, I know that this opens 180 degrees. As long as it's a straight line, it's going to be a 180 degree angle. Now, very similar to that, a linear pair are adjacent angles. Adjacent means next to each other, so it's going to be two angles that are next to each other and share a ray. adjacent angles on a straight line. So that's like the diagram right here. These two angles are linear pairs. 130 and 150 are linear pairs. So another just diagram of this. So there's my straight line, and this angle number 1 and this angle number 2 are linear pairs. Linear pairs is what you recognize from the diagram, and then what results from being a linear pair is that they are supplementary. Supplementary means that the two angles add to 180 degrees. So these two angles are not only a linear pair, but they are also supplementary. So if I draw that similar diagram, this is angle 1 and angle 2, I can say that the measure of angle 1 plus the measure of angle 2 is 180. So these three are very similar to each other. You start by being a straight angle, you split the straight angle into two linear pairs, and then what's true about the linear pair is that they are supplementary. They add to 180. In similar fashion, the opposite of supplementary is complementary. Complementary is two angles that add to 90 degrees. So that would be this picture where we've got a 90-degree angle, but I'm splitting that angle into two parts, not perfectly down the middle. This is angle 1 and this is angle 2. Those two angles are complementary to each other, meaning that the measure of angle 1 plus the measure of angle 2 is 90. And then we can say that if these are complementary, you can go back and forth. You can talk about the fact that it's a right angle. A right angle is just an angle with a measure of 90 degrees. So that can be any, perpendicular lines make 90-degree angles. So anything that's got that box description, anything that makes a sum of 90, or any two adjacent angles make a 90-degree angle. Now, supplementary and complementary do not have to be next to each other. These are just the ways that they typically come at you. Also, a memorization technique that students have used is that complementary, the first letter is a C, and supplementary, the first letter is an S, and C comes before S in the alphabet, so that's the smaller one, and this is the larger one. So now let's use some of this knowledge to help us prove something that's true about vertical angles. It says here are two intersecting lines that create two pairs of vertical angles. Well, we've seen a diagram similar to this in the warm-up. We should have noticed that some things were true. What is your conjecture, or what is your thoughts or thesis? What's your ideas about the relationship between the vertical angles A and C and D and B? Go ahead and pause the video and write down what you think is true. From the warm-up, most of you probably recognize that it looks like A is equal to C. Looks like those two are the same. And then it also looks like D is equal to B. You'd be right. That's true. That's what's true about vertical angles. But let's talk about how you could show that to yourself. One way that you could show it to yourself is using a protractor and measuring. That's one way. A second way is using tracing paper and using transformations. So if I traced this angle here, angle C, and I rotated angle C and it landed on angle A, then I would have a transformation of rotation, a rigid transformation that moves angle C onto angle A. Or I could think about it as a rigid transformation of reflection. So if I drew in a line of reflection down D and B, I could see that angle C perfectly reflects onto angle A using tracing paper, just using my eyes to see that it's a reflection. So tracing paper shows us transformations, rigid specifically, because if there's a rigid transformation between the two of them, then they are congruent. We know they're the same size. We know they're equal. So those are some ways that you could prove just to yourself that this is true. What we would like to do today is answer this question. How do I know that this conjecture, how do I know that these are true for any vertical angle without using a protractor, without using tracing paper, without drawing in a line of reflection? It seems like this is true for everything, but mathematically, how can we show that? One way that you can show it is using some knowledge of the diagram that's also true. So what do we also, like we're trying to say that A equals C. This is the one I want to focus on. Because if we can say that A equals C, then we can also show that D is equal to B. This is what we want to show, right? We want to show that A equals C. But what else do we know is true about this diagram? So like, what do I know, like if I cover it up on the top here, what do I know about that part of the diagram? What can you say is true about A and B? Oh, well, they're a linear pair. They're on a line together and they're supplementary. So let's just write down that statement that I know that that's true. A plus B is 180 degrees. Well, what else can we say is true? Which other angles are on a linear pair? If I cover up those two angles, I can see that both C and B are a linear pair. So I can say C plus B is 180. Well, now look at these equations. A plus B is 180 and C plus B is 180. What do these two equations have in common? Well, I can see that they're both equal to 180, and I can see that they both add a common angle of B. And you can see that, like if I'm thinking about going around the figure here, I can see that that total angle between C all the way to A has a commonality of B. I could have gone the other direction as well. I could have had a commonality of D in place. So this is not the only way to write this. So you could have showed that they had a common angle of D. Well, if this is true, if A plus B is 180 and C plus B is 180, then they're equal to each other. So I can take this whole expression of A plus B and C plus B, and I can say A plus B is now in fact equal to C plus B. Oh, well, I'm trying to show, look back at what we're trying to show. We're trying to show that A equals C. Well, A plus B equals C plus B. What's the same on both sides? Oh, well, I've got B on both sides. That's the commonality. So if I subtract B mathematically from both sides, the B's cancel and we show that A equals C. So this was a generalized proof. This is the first one that you've ever seen. This is an equation style proof, a direct proof where you are trying to take knowledge that's true about a mathematical diagram and show it using equations to show that it's true for all cases. So now let's define vertical angles. So the vertical angles are angles that are not necessarily in the vertical format. They can be horizontal as well, like D and B are vertical angles. And what's true about them is that they're congruent. But also, they are, just to define where they are, they're angles across from each other on an intersection. So that's like the diagrams we've been looking at. This would be angle 1 and this would be angle 2. And we can say that the measure of angle 1 equals the measure of angle 2. So now that we tried this on our first time of doing a proof, I just want to highlight what is the difference between one example of something being true and a proof for all cases. So looking back up at our warm-up, this first example, or even really this second one, like vertical angles, this is a specific example using numbers. 150 and 30 and 150 and 30 is a specific example of vertical angles being equal. But does this include every case of vertical angles? No, But when I generalize it and I use variables that could be replaced with any number, that's when it becomes a proof. That's when you can start generalizing things. So one example is usually using specific numbers, where it's just one specific example. But if you're going to write a proof for all cases, you generalize. And typically you use variables, because you're trying to say for any case, for any number, that this is true. All right, go ahead and pause the video and write down, what do you notice and what do you wonder about these three diagrams? Something that you might notice that there are dotted lines and solid lines. You might also notice that there's a horizontal line in every picture. You might recognize that the solid lines represent linear pairs. Something that you might wonder if the dotted lines make 90-degree angles. You might wonder if these dotted lines are maybe angle bisectors, cutting each angle in half. Again, go ahead and pause the video and read through this task statement here. This can't be right, can it? Here's a figure where ray meets line L, and the dashed lines are angle bisectors. They are telling us that they are angle bisectors. Now, a student, Diego, made the conjecture, the angle formed between the angle bisectors is always a right angle, no matter what the angle is between R and L. Thinking back to the what do you notice and what do you wonder, it's a very similar diagram. The angles change each time on the linear pairs. It says it's difficult to tell specifically which angles Diego is talking about in his conjecture. Label the diagram and rephrase Diego's conjecture more precisely using your labels. I recommend that you use letters instead of the numbers, because we're going to be starting to talk about angle size. So I'm going to call this angle A. I'm going to call this angle B. This one angle C, and this one angle D. So what are we trying to say? We want to rephrase using the angles. Diego is trying to say that angle between the dotted lines is 90 degrees. So he's trying to show that B plus C is 90. That's what we'd like to show. So then, is the conjecture true? Well, it feels true. These all look like 90 degrees too. This looks like a 90, this looks like a 90, and this looks like a 90. So then it says, explain your reasoning using the knowledge about angle bisectors and straight angles. So let's start with knowledge about angle bisectors. What do I know is true about angle bisectors in this diagram? Well, I know that this angle A and this angle B are the same size. I can draw arc marks to show that. So I can say that A is equal to B. And then I also know that this dotted line is an angle bisector, so I could say that this angle C is congruent to this angle D. So we can also say C is equal to D. Now they want us to say, what do we know is true about straight angles? Well, I've got this straight line here, so I can say about straight angles, I can say that A plus B plus C plus D, 1, 2, 3, 4 parts are all on the straight angle together, and that total sum is 180. So now we're trying to show this. Just a B plus a C equals 90. I've got some parts here. I've got a B and a C, but then I also have an A and a D, and those are equal to 180. But I know that A can be replaced with B. They're the same. And I know that C can be replaced with D because they're the same. So we're going to work from this equation and work down to try to show that B plus C equals 90. So which letters are not part of the final equation? Which one's not part of the show? Well, it doesn't have an A and it doesn't have a D. So these are the two that need to go away, and I also need to turn this 180 into a 90. So what can I say is true about A? Oh, well, A is also B. And what can I say is true about D? Oh, well, D is also C. So now my equation could be this. A gets replaced with a B plus B, and then still plus C. And then D gets replaced with another C. So plus C equals 180. Oh, well, now I've got two B's and two C's is a 180. That's pretty close to B plus C equals 90. What's happening is that it's half the size. So now mathematically I could say two B's and two C's is 180. Oh, we're getting closer. But what do you recognize about each term to get to 90? Oh, we can divide each piece by 2. And now finally, B plus C equals 90. Check. Go ahead and pause the video and try these check your understanding problems on your own. Without a protractor, what is the measure of JMQ? Well, JMQ is a vertical angle to 125. So I know that JMQ is 125. And what is the measure of QMK? QMK is a linear pair to 125. So 180 minus 125 gets us 55. So then this angle is 55. And then its vertical angle across from it is also 55. Select all the true statements about the figure. We've got a C, B, A, and D similar as above. We've got lines intersecting. The first one says B plus C is equal to D plus A. Oh, that's true because these two are 180 and these two are 180 and they're equal to each other. So that one's true. All right, this one's talking about transformations. Rotate 180 degrees using the center B. Then the angle ABC is the image of EBD. Well, that's true too because these are vertical angles and a 180 degree rotation will spin that around onto itself using a rigid transformation. C minus D is 90. C minus D is 90. Well, I don't know that that's true because I don't know that this is a 90 degree, so that one's not true. A plus B is 180. A plus B is 180. Well, that's true because those are a linear pair. Reflect across line AD, then angle ABE will be the image of DBC. Oh, well, that's the wrong line. It should have been across this line through the middle, so that's not true. Rotate clockwise CBD using center B, then EBD will be the image of ABC. Well, I know that CBD and ABC are not even the same size, so that one is also not true. Thank you.